Okay, well, thanks everybody for joining us today. The second of our fall 2021 seminar series for Space of ET. And today we have Aishwarya Kumar, who's going to be presenting on waves and tides and things that, at least in my group in SuperDarn, we've looked at some of this in here on Earth, but it'll be interesting to hear of the different perspective of our closer planet neighbor of Mars. So without further ado, take it away.
Thank you, Dr. Stern. Hi, everyone. My name is Aishwarya Kumar. Like Dr. Stern mentioned, I'm a graduate student in the Aerospace Engineering Department, and I work with Dr. Scott England. Some of you may know me from Space at PT, some of you may not. But today I'm going to be talking about some of the work that I've been doing for the past year and a half. And the title of my talk today is Observations of Atmospheric Tides in the Martian Middle and Upper Atmosphere with MAVEN and MRO. So before we get into the specifics of the work I've done and the results that we've obtained, I'd like to spend some time talking about Mars and why we care about this planet. So on the slide here, this figure shows basically, it compares the atmospheric compositions of Earth and Mars. Before I get to this figure, I just want to talk about, why do we do comparative planetology? We could very well study the climate and meteorology of the Earth without studying any other planets, but by looking at other planets and planetary atmospheres, it gives us this opportunity to test our theories and our general understanding of physical processes and their interactions, but in a different environment with diverse forcing functions and boundary conditions. So Mars has always played a prominent role in this comparative study because it shares these fundamental characteristics, properties like rapid rotation rate, relatively thin atmosphere with the Earth, and it also has a similar axial tilt. So this figure here compares the atmospheric composition of both planets, and for the Earth, as we know, the primary constituent is nitrogen, followed by oxygen. On Mars, this was first determined in the mid-1970s by the Viking landers. And we see that CO2 is the principal constituent, followed by nitrogen, argon, oxygen, and carbon monoxide. So now let's take a quick look at the thermal structure and how this compares to that of the Earth. So as you can see in this figure on the left, shown here on the right side of this figure is the temperature as a function of altitude for the Earth, and right besides is for Mars. So one of the first things that we do notice is that the temperature decreases with height, both on Mars and Earth, but this stratosphere region that we have on the Earth is not existent on Mars because it lacks an ozone layer or any other strong enough absorber in this regions. So we also see that the surface pressure is very low compared to that on Earth. It's about less than 1% of that on Earth. And lastly, this profile here that's shown by these dashed lines is the temperature profile when the Martian atmosphere is dusty. So on Mars, additional heating of the atmosphere comes from the absorption of solar radiation by suspended dust particles. So this you've probably heard about dust storms on Mars. So this is dust lifted from the surface of Mars due to strong surface winds. And many dust storms occur each Martian year. And they're generally classified based on their size. Now, these dust storms can last anywhere between a few minutes to a few hours, or even planetary encircling dust storms can last for months and occur quasi-annually. So this is just a small GIF from the 2018 Martian dust storm. So you can see, I think it kicked off around mid-June, July 2018, and you can see the difference between the planet before and after. And this dust storm is what actually caused the NASA Opportunity rover to lose contact with the Earth. So dust storms are a very interesting and important phenomenon on Mars, and something that needs to be considered when you're studying the dynamics of the atmosphere of Mars. So now that I've hopefully established some interest and motivation to study Mars and understand the atmosphere of Mars, I'm going to talk about waves in the atmosphere of Mars, and specifically atmospheric thermal tides, this type of wave. So just like we have waves in the ocean, we also have waves in the atmosphere, and they have a great influence on the dynamics of a planet's atmosphere. So depending on their scale, we can classify them into different categories like gravity waves, atmospheric tides, or planetary waves. So this study I am going to discuss today specifically concerns with atmospheric tides. So we're going to focus on that. In the literature, tides are referred to as thermal tides or atmospheric thermal tides, or even just atmospheric tides. And this is because these tides are a response of the atmosphere to the cyclic absorption of solar radiation by a rotating planet and its atmosphere. So this leads to global scale oscillations in different atmospheric fields like temperatures, winds, densities, and so on. So mathematically, they can be represented as shown in equation 1 here on this slide. So A stands for the amplitude of the oscillation, Z stands for the altitude, theta is the latitude. There's capital omega is the planetary rotation rate, T is the universal time, lambda is the longitude, and phi is the phase of the wave. So N here stands for the temporal harmonic, or how many cycles do we see in a day, or in the case of Mars, a sol is what a day is referred to. And S stands for how many cycles do we see per 360 degrees in longitude. So another term that I just want to put out there is N is equal to 1 refers to the diurnal component of the tide. N is equal to 2 refers to the semi-diurnal component. So that just means 1 cycle per 24 hours or 1 cycle per 12 hours. And eastward or westward propagation is denoted by S less than 0 or S greater than 0. So broadly, atmospheric tides can be categorized into migrating tides and non-migrating tides. So let's take a look at what these are. So migrating tides are usually the strongest tidal modes, and they move westward at a rate of 360 degrees longitude per sol. In other words, they are sun-synchronous waves. They are strong, they have a strong presence in the lower and middle atmosphere. They do not vary with longitude. So going back to the slide here, or if you look down here, the equation 2 is similar to the equation 2 that was on the previous slide, which I didn't discuss earlier, but this is a wave represented in a fixed local time reference frame. And when we look at a wave from a fixed local time reference frame, the wave number is actually Doppler shifted to this S minus N in longitude. And so migrating tides are these longitude independent waves, and S is equal to N in this case. And so this little video shows you what migrating tides look like. So the red dot here is the observer, and I'm going to play that again. And as the Earth rotates under this high pressure and low pressure region, the observer sees one peak and one trough. So non-migrating tides, on the other hand, can propagate either westward or eastward. They can travel faster or slower than the apparent motion of the sun in the sky. And they can vary with longitude in a fixed local time. Now, these oscillations are produced by different sources, but on Mars, one of the primary mechanisms through which they are produced is by topographic modulation of solar radiation absorption. So let's look at that little video now. So we see the high pressure and low pressure region is also moving in the opposite direction as, I'm sorry, in the opposite direction as the observer. And so now the observer sees two peaks and two troughs as they rotate with the planet. So why do we care about tides on Mars? So in this slide, we're just looking at, tides have been observed previously on Mars by multiple observations and spacecrafts, mostly in the lower and middle atmosphere. So on the left side, we have a plot of one of the first observations from the MGS spacecraft. So these are longitudinal variations in densities that are shown at 125 kilometers, which is near the lower bound of the thermosphere on Mars. And we see that this variation is mainly characterized by wave number 2. And they showed that this amplitude variation has value of 22%, which is quite a bit. On the right is a more recent study done by the MAVEN mission. And here we see on the left panel is the CO2 densities, the neutral densities that are being compared to the electron densities on the right panel. And what they see is comparable wave numbers in both the neutral densities and the electron densities. They see wave number 3 dominant in both of these. And so this is interesting because it begs this question: how do things compare at higher altitudes to what's going on down at lower altitudes? So tying this previous work to the motivation for the work that's being presented here, currently we have observations from multiple spacecrafts. So on the left, we have this infographic showing the current active solar orbiter missions on Mars. And out of these, we use observations from two missions, the MRO mission, Mars Reconnaissance Orbiter, and the MAVEN mission. So we will be focusing on the middle and upper atmospheric region. So the figure on the right compares the height ranges of the MRO and MAVEN atmospheric observations. So we use data from the Mars Climate Sounder instrument, which is an infrared thermometer, radiometer, and it covers this region from 0 to 90 kilometers, which is the lower and the middle atmosphere. And IUVS, which is a spectrograph, covers the majority of the upper atmospheric region, but we also have this observation at 90 kilometers, which are temperatures that are derived in the middle atmosphere, which gives us a good comparison to this MCS observation here. And lastly, we have NGIMS, which is a mass spectrometer that gives us CO2 abundances or CO2 densities and allows us to compare to the IUVS high altitude observations. So MCD, Mars Climate Database, which is marked over here, is a database of statistical parameters that we get from the general circulation modulation of the Martian atmosphere. And this is like a model simulation result that we will be comparing to our observations. So what are the objectives of our study? So we want to compare tides observed at different altitudes. This hasn't been really done before, where we've tied in observations at different altitudes. Most observations have been taken place in the middle atmosphere, the lower atmosphere, and some recent observations of the upper atmosphere. But by looking at different altitudes, what we'll be able to do is we'll be able to see which waves reach the Martian upper atmosphere from the lower atmosphere. We do this by looking at the same local time in a fixed narrow latitude band and at different Ls of S. So Ls of S is just season. So we're just looking at different seasons by fixing local time and latitude across all 4 data sets from the 4 instruments that we have. So we want to separate out seasonal effects from latitudinal effects. Hopefully infer some tidal dissipation by comparing the wave amplitudes at the different altitudes that we are sampling. We look at the year-to-year and seasonal consistency of the results. So are these tides unique? Are they repeatable at a particular place and time? And we'd be introducing this new IUVS derived temperatures at 90 kilometers, and we'll compare this to the MCS data near 90 kilometers. And lastly, we'll compare all these observational results at different altitudes with the model's results and see how well the model compares to these observations. So now I'll talk about how do we choose our data? How do we select this data? So MCS, which is the infrared radiometer, has a pretty even data coverage. And so we will let MAVEN drive this data selection instead. On the left is a figure of the NGIMS data coverage between 130 and 250 kilometers from the year 2015 to 2018. Each of the colors just denote a different month. So the data is chosen by defining this latitude and Ls of S or season box in a fixed local time. And we make sure that it has repeated sampling over several time periods during the MAVEN mission. And so it has both IUVS and NGIMS data. So IUVS and NGIMS is again the high altitude observations. And we know again that MCS data is always there. So this also means that we'll only be using dayside data because IUVS does not consist of the required data during the nighttime. So by doing this, we end up with 2 regions, one in the northern hemisphere shown by region 1 and one in the southern hemisphere shown by region 2, each of which is sampled 3 times. And we refer to these 3 time periods in each of these regions as cases A, B, and C. So for these data sets, we also have the IUVS level 2 data and the derived temperatures at 90 kilometers, which we are introducing in this study. So now that we've looked at how we select the data, I'm going to divide our analysis into 2 regions, the low altitude observations and the high altitude observations. And then we'll combine and compare them together in the end. So here we see on the left side is the figure of the MCS data, which is similar to the data coverage shown for the NGIMS in the previous slide from 2015 to 2019. And on the right, we have the data coverage as a function of latitude and local time only for Northern Hemisphere case A. So this is one of the cases that we got out of our data selection process. So we will use this case as an example to go through the analysis and results for from each of the observations from each of the instruments. So the black boxes here on the plot on the right side shows us the latitude and local time ranges that we've chosen for this analysis. So generally, from the spacecraft orbit, or because of spacecraft geometry, it allows us for observing only this S minus N wave number. So as you can see, I've just put the equation 2 at the bottom over here again. So from spacecraft orbit, which is a fixed local time reference frame, what we're able to see is this wave number S minus N. We would ideally like to separate these and know what the values of S and N are individually. We can do this using the MCS data. IUVS and NGIMS only allows us to look at the S minus N wave number as a whole. And this is another reason that motivates using multiple instruments in tandem. So how are we able to look at this S and N separately? So what we do is we take this data from those two boxes at two different local times. And because they're roughly 12 hours apart over here, we can separate the diurnal components, which is the 24-hour components, from the semi-diurnal components. So what we do is we add the temperatures from these two boxes and we subtract the temperatures from these two boxes. And so what we get is this wave field over here. So shown on the left is the reconstructed wave number 2 and wave number 3. For the top panels are the sum and the bottom panels are the difference. And what we see is that at the higher altitudes between about 70 to 90 kilometers, wave number 2 is the dominant wave number. In order to identify the wave numbers from these structures, we use a simple least squares fit using a set of superimposed sinusoidal harmonics and a mean value. So now we go on to compare these MCS observations to those IUVS observations at 90 kilometers. So how do we even have these observations at 90 kilometers from the IUVS? And this is because we have this mid UV feature coming from the photodissociation of CO2. And this is not yet a data product, and we got this from one of our collaborators. And so this provides an excellent opportunity for us to compare these observations near 90 kilometers with the MCS, which is also near 90 kilometers. And what we see in this case is that wave 2 dominates by far, and the diurnal component dominates by far. So you can see over here, the table at the bottom compares these IUVS wave numbers to the MCS wave numbers. And the MCS, as you can see, is split into this sum and difference. So the difference gives us the wave amplitudes for the diurnal components. The sum gives us the wave amplitudes for the semi-diurnal components. And we see that the diurnal component here, 4.51, it's much stronger than the semi-diurnal component. Now, we also compare these to the model that we spoke about earlier. So these shown here, the top panels are again the sum and the bottom panels are the difference for three heights at 72, 80, and 88 kilometers, both from the model and data. And we can see that both of them agree with the wave numbers. The phases may not be perfectly aligned, but the wave amplitudes are comparable, and the wave numbers are similar. An interesting thing that we see with the model is that here, as you can see, the semi-diurnal component is a little stronger in the model than it is seen in the observations. But overall, this is a good result because we see that the model seems to agree with the MCS at low altitudes. So now let's just put all of these together and see what it looks like. So this table summarizes all the low altitude results. So from left to right, we have the observations from IUVS and MCS, but they're also compared to the model. So we also do model run simulations for 90 kilometers, just like we did with the MCS. So what we see is that the observational results agree very well, and we see for the same time period, wave number 2 to be dominant and the diurnal component is strong, while we see semi-diurnal components mixed in some cases. So in addition to this, this column right here, which shows MCS Mars year 28 to Mars year 34, what we do is that we look at the same latitude and local time, and we look at the same LSOFS or same season, but for different Mars years, and then we've averaged it all together. And what we see is a consistent year-to-year picture for this specified season and for all Mars years. Because you can see here that the wave number 2 is dominant, and the mean temperatures also agree here. So you can have 146 Kelvin and roughly 146 Kelvin for the Mars year that we're looking at here as well. So now let's look at some of the high altitude observations. So first I'm going to show you the NGIMS, which is the mass spectrometer for Northern Hemisphere case A. So NGIMS gives us the CO2 abundances. And the figure on the left is a plot of the CO2 abundances as a function of longitude and altitude. And what we see here is that this wave 2 kind of structure with 2 peaks, one near about minus 120 degrees and one near 90 degrees. So what we then go ahead and do is we sample these at just 165 kilometers and 175 kilometers. So these are bins centered at these altitudes. And on the right, we see these wave structures at these altitudes. And so each of these dots are the orbit averaged abundances. And just as we did with the MCS, we do a least squares fit. And even for this case, what we see, and we'll see it later in the table, is that the NGIMS also shows us a dominant wave number 2 at these altitudes. And now we look at the IUVS. So this is the imaging ultraviolet spectrograph. Now, the IUVS gives us both CO2 densities as well as temperatures. So, So on top here, because I didn't show this earlier, but this is all the data coverage we have from the IUVS from 2015 to 2018. At the time of doing this, starting this analysis, there was no 2019 data for this specific densities and temperatures. So on the right, plot B shows us Northern Hemisphere case A, the data that we have, and each of these little orange and blue boxes show the scans taken by the IUVS instrument. C and D show the densities and temperatures respectively at 140 and 150 kilometers. In the densities, you can see this clear wave 2 structure in at 140 kilometers, but there is some other wave component present clearly because there's some asymmetry that we see in this wave structure. So this leads us to slide 19, which gives us a summary of what the high altitude results look like. And so what we see is that for the high altitude cases, the model doesn't agree very well with the observations. The observations agree within themselves. We see the IUVS temperatures here, the IUVS densities, and the NGIMS densities all see wave number 2. But the model fails to capture this. The model seems to see wave number 3. Although the second strongest wave is wave number 2, there is also a big difference between the mean temperatures and mean densities seen by the model and the observations. So all in all, for the high altitudes, the model doesn't seem to be capturing these waves very well, at least not at these particular altitudes we're looking at. So to summarize briefly, what we see in the Northern Hemisphere is that the mean temperatures for the MCS, so the MCS is looking at the lower and middle atmosphere up to 90 kilometers, show a consistent like year-to-year picture with almost constant mean temperature for the LSFS that we are looking at in this case, and for all the other Mars years. We see a good agreement in the mean temperatures as well as wave numbers between the IUVS at 90 kilometers and the MCS at near 90 kilometers. The amplitudes of the wave numbers don't agree. We see much bigger amplitudes with the IUVS, but this is probably because of how we are analyzing this data. We use a different method to look at the IUVS and a different method to look at the MCS. Overall, we see a dominant wave number 2 in the Northern Hemisphere. In most cases, we see that the diurnal component is stronger and the semi-diurnal is mixed in some cases. Although we do see other wave numbers, the amplitudes of these are much lower. So for the Northern Hemisphere, given the past several years of data, we can predict what next year would look like given a specified a specified season. At the lower altitudes, sometimes we see a phase difference between the model and the observations. And this is probably because of the vertical wave propagation in the model. We're still investigating these differences that we see between the model and the observations at the high altitudes. Now, for the Southern Hemisphere as well, we have 3 cases A, B, and C, just like we did in the Northern Hemisphere. But we have a few caveats when we are looking at the Southern Hemisphere. The MCS data runs out at about 82 kilometers, so we can't go all the way up to 90 kilometers. And for some of these cases, the latitude ranges have been moved in order for us to have sufficient data to do the analysis. So what we see in the Southern Hemisphere, these are the low altitude data. So this is IUVS and MCS at 90 kilometers, near 90 kilometers. Wave number 3 is the dominant wave number. And we see that both IUVS and MCS observations agree well. Model and observational results also seem to agree, where the model also picks up a strong wave number 3, as can be seen here. Year to year, also we have a consistent result looking at this column right here, where the mean temperatures seem to agree given the specified season for the different Mars years. Now, looking at the high altitude data here, we see that again, wave number 3 is dominant. The model seems to agree here for some of the cases with the observations. IUVS seems to be picking up both wave number 2 and wave number 3 in its temperature data. But NGIMS here sees a strong wave number 3. The model seems to be picking up wave 2. So there's this disagreement with the NGIMS model and observations. So to summarize, Southern Hemisphere in general, in all our Southern Hemisphere cases, we see a wave number 3, but there are different wave numbers that are mixed in more so than the Southern Hemisphere. Past years of data for the MCS shows agreement in wave amplitudes and mean temperature. So MCS is the low altitude near 90 kilometers. Southern Hemisphere case A and case B, which we don't have any dust storm for, we see an agreement between the low altitude IUVS and MCS near 80 kilometers. And with the high altitude results about half of the time. Southern Hemisphere case C, which happened to be a dust storm case, not completely, but half of this time period is filled with a dust storm case. So our assumption falls apart here because our data neither lies completely before or completely after the dust storm. And so we cannot put all of this into a common analysis. So in general, what we learn looking at the Southern Hemisphere is that this region requires more observation. And I'm I am currently just writing up all of this work and finishing up some vertical propagation related work for this research. And this is all I have for you today. Thank you. I will leave you with a slide of some amazing pictures taken by some spacecrafts and data from Mars. Thank you.
Alrighty, well, thank you very much, Aishwarya. I'll open it up here. Any questions that we might have? Either feel free to say unmute and ask, or put them in the chat and we can relay them if you need to. I'll maybe ask one. It seemed like I was trying to follow there. There was a lot of information to try to digest.
Yeah, I was trying to. Yeah.
But in general, it seemed as though there's a little bit of a disconnect between the northern hemisphere and the southern hemisphere.
Yes, and most of that arises, I think, like from the fact that you can actually see in this figure here how the topography changes from the northern hemisphere to the southern hemisphere. The southern hemisphere is much more like higher altitude and has like a lot of variation, and a lot of these non-migrating tides that we're seeing on Mars are modulated by this topography. And so we expect to see kind of this difference in the waves that we're seeing in both hemispheres. We also expect to see them change by latitude. So I'm looking at these regions close to the equator. And so the other study that I'm going to try and look at is this high latitude data, and that will be interesting because we don't really expect to see the same kind of waves at those latitudes.
Gotcha. Well, very cool. Yeah, I guess I was wondering with the color scale there, but I guess you can kind of make out from highlands and lowlands, it's a altitude.
Yep.
Kind of difference. So any other questions from our folks that have joined us today?
Yeah, let me pop up with one. Oh, Julian, I'm sorry I cut you off.
Yeah, go ahead.
Go ahead, Mike.
What are the longest periods that you found with either tides or say waves, like planetary waves?
Oh, planetary waves wise, I think like there are the 1 day and 2 day planetary waves that are seen, but I am specifically looking at tides. So the longest period that I am looking at is 24 hours.
Okay, it's actually a little longer, right? Because
Yes.
the Martian day is.
Yes, it is. It is slightly longer. That's correct. Yes.
Okay, thank you.
Yeah, Shirley, you had a question too?
Yeah, I'm gonna be asked. Yeah, I'm not sure if there's a good answer to this question or not. Yeah, since I'm interested in electromagnetic waves, just wondering if there are any instruments on either of the satellite you mentioned can measure the electromagnetic wave, if there's any there.
Maybe there might be instruments on MAVEN. There's about 9 instruments. Okay, there we go. There are 9 instruments on MAVEN. I actually have, if you give me 1 second,
Sure.
I might have to go to my very last slide. It has MAVEN and all its instruments listed. Okay, there we go. So MAVEN has a lot of instruments that looks both at the atmosphere and also looks at the sun. So you might find like some of these instruments that I think the MAG or the SWIA where electromagnetic waves might be measured.
Okay, so max probably measure the magnetic field.
Yeah.
Okay, I see. Thank you.
I have a question in the chat. Do the equatorial regions experience wave interference because of the difference in the waves in the southern and northern hemisphere? So can you tell me what you mean by wave interference? Do you mean
Maybe I can kind of paraphrase there for Dylan. I think the idea is if there's differences between the northern and southern hemisphere, right, at some point they have to combine. And so is there kind of strange kind of interference that goes on in that equatorial region? Maybe have you looked at that?
So yes, there have been papers that look at these waves closer to the equator, and at least one of the papers that look quite close to the equator, about 10 degrees, I think, 0 to 10 and 0 to -10, see wave 2 in both regions, which is interesting. There's no difference between that. But I'm looking slightly away from that. So I'm looking at about 15 to 25 north and south. So I think that's where that maybe that topographic difference comes in, and we see this difference in the waves.
Okay, I think that's a pretty good summary. So, yeah, any other questions here?
Hey Ash, real quick.
Yes.
What issues have you had as far as like data collection from the actual satellite itself, if you've had any? I mean, as far as maybe the distance between us and the satellite, or communications errors, or just instrument error?
Okay, very interesting question. Because I'm working with different instruments, if we just look at the MAVEN mission, right, it's got 9 instruments on there. And I'm looking at the spectrograph and the mass spectrometer. And the mass spectrometer takes its measurements along the spacecraft velocity vector. Whereas, the spectrograph is looking off on the side. So, when those slides that actually show the data coverage, so that's the imaging spectrograph, ultraviolet spectrograph. So you see how there's almost no data here at these latitudes beyond 7 a.m. and after 7 p.m. And what it looks like here, if I go back to NGIMS, is I have this kind of spacecraft track, spacecraft velocity vector kind of data observations. So one of our challenges has definitely been kind of stitching this data together. Of course, it would be really nice to have more data and multiple data sets that do overlap in latitude, longitude, and in time. To get like the whole tidal spectrum, ideally you want like all longitudes and all time coverage. But unfortunately, we don't have that. And so kind of working with what we have and pulling out, even this gap that we have between 90 kilometers to about 140 kilometers, I would say. There might be a lot of things happening there. It's a very interesting region as well. We want to see if any of these waves do make from like this region up to this upper atmospheric regions, if they're the same, if their phases match, we would expect their amplitude to grow. And do they dissipate in any of this, and in this region, or higher up? So all these things with data constraints come in. Hopefully there's a couple of other data sets that might fill in this gap that I may look into later. But yeah, those have been like my issues with this project, at least. Kind of figuring out how to put all the data together and get it to work.
Cool. Yeah, thanks for answering that.
And maybe sort of a similar question, and maybe I missed it somewhere. I did see, back that the MAVEN, got there in 2013, or was launched in 2013, got there and hit to Mars in 2014. It's quite a ways in the past, and sometimes it still have long lifetimes. Is there still data being generated that's valid, or?
Yes, there is data being generated. They are doing, there are different like science goals that they focus on, and their measurements of, which instrument gets more time has changed. But I think there's actually good data right up to 2020. Yeah, that's what I got from the last like MAVEN meeting, that they're going to continue. It's more like a funding by year thing. So if they can extend it by every year, and after that, if it gets decommissioned, I guess like they're just going to go with whatever data they can get.
Yeah, I sort of asked that too, is sort of a thing that we looking for in Earth is the upcoming solar cycle is starting to spike again, right? And so on Earth there's some kinds of things about how solar cycle or solar activity kind of influences those kinds of things, even down in the other all sorts of regions of the atmosphere. So I'd say that's a good kind of a comparison too, that can give some data, as far as solar kind of quiet times, that we've come through on the minimum, and then if it can continue on through, maybe another solar maximum, or at least like an uptick in activity. So
Right.
very good. So cool. Last call for any other questions. These have been really good. Going once, twice. People should be able to reach the mute button by now. Thank you again, Aishwarya, and thank you for such a great one. It's a lot of good questions here. So thank you very much. Thank you everybody for joining us. We'll have another one here coming up, another seminar in 2 weeks. And that one is scheduled so far from the UTPROSAT team. So we'll be hearing about the latest of VT students and graduates, students in their reaches into space here in 2 weeks. So thanks everybody for joining, and then we'll see you then.